This is number 8 from the review problems, and this is about a spring. This is an energy problem. And so the spring shown in the figure is compressed 50 centimeters and used to launch a 100 kilogram physics student. The track is frictionless until it starts up the incline. The student's coefficient of kinetic friction on the 30-degree incline is 0.15. Draw a clearly labeled energy bar chart for the spring student system at point A, which is before the spring is released, at point B, after the spring is released, at point C, which is at the bottom of the hill, and then at point D, which is the max distance he can go up the hill. Next, we will find the student's speed just after losing contact with the spring, and then we'll find how far up the incline the student goes. So let's start with our givens and finds. So we have our delta x spring is equal to 50 centimeters. We have the mass of the student is equal to 100 kilograms. I wonder who that would be, which student I would launch. Next would be mu k is equal to 0.15, and theta is equal to 30 degrees. Okay, and so for find, we want to know the speed right after they're launched from the spring and how far up they go. So we'll call that delta L. Okay, and so delta L, what we're going to do is we're going to say delta L is this distance here, along here, because I'm using delta x for the spring, so I just don't want to confuse my variables. So delta x is going to be how far up the hill the student goes. So if I draw my picture, it's going to look something like that. And my spring is here. And I'm just going to make the student into a block. That just is a little easier. And I know that they're going to be, like if I continue this through, right, this is going to be right after they're launched. So I'm going to say that this is position A, where the block is like right here. This is position B. This is position C. And we'll say this is as far as it goes up. And this is position D. So I've got A, B, C, and D. Okay, and so I need to create my energy bar chart. So this is kind of a before and after, right? And then I'm going to have a before and after here too. So this is going to be there, and then I'll have my block like here. So I've kind of got a couple before and afters. A to B, that's when I find the velocity right after it's released. And then another like before and after here and here. Or I could think about just say from here to here. So my before and afters, I can pick what I want for how to use the energy equation, which we'll talk about a little more at the bottom. So let's do my energy bar charts first. So if I think about this as my 0 point, so this is going to be like my y equals 0, the person, the student has potential energy, gravitational potential energy, and spring energy. So I'm going to have, say, spring energy, and I'm just going to be consistent. I don't know exactly, so this is going to be called U spring and U A. So just at point A, and this is at point A. And then I'm going to have kinetic energy at A and E thermal. But I don't have anything there. So that's going to be this is A. And now B, if I think about B, I'm not going to have any more spring energy, but I'm going to have kinetic energy because I'll have velocity. So I'm going to have nothing for U spring B. I'm still going to have the same amount of potential energy, so hopefully I can draw that. I can eyeball that. It's about the same height as that. So that's U, B, and I'm going to have kinetic energy. The rest is kinetic energy, so that's going to be my K, B, and I don't have any thermal. that's B. Now C, so at C I'm down here. I don't have any potential energy. I'm at the bottom of the hill. I don't have any spring energy, but I have a lot of kinetic energy. So U spring C, U C. So this is my spring potential, my gravitational potential, and then I have KC, which I have a lot of. So I have to make this height as tall as the other two together. So I'm going to go with like something like that. And then I don't have any E thermal. So that's my C. And then my D is, I've got some, so I'm going part of the way up the hill, probably not all the way, right? Because I'm going to be losing some of my energy due to friction. So I have no U spring. I have some UD, so some gravitational potential energy. But it's not going to be as much, so I'm going to go a little lower. I've stopped, so I have no kinetic, but then I have, the rest is E thermal. So make that like something like that. So it's taller than this one because these two added together, this is smaller, so that one's got to be a little taller. So this is my E thermal. And so this is the energy that I lose due to friction, because there's friction on this surface, and that's using up some of the energy. So I've got my final energy is the potential energy, gravitational potential energy, plus the energy that I lose due to friction. So that was A, right? And so B, what's the student's speed just after losing contact with the spring? So what I'm going to do here is I'm going to say my initial energy is equal to my final energy. And so what initial energy do I have? Well, I know I have, if I look at my energy bar charts, I know I have the spring energy and I have potential energy. So that's what I have initially. So I'm going to say U spring plus UA plus, so right off here, my kinetic energy at A is equal to U spring, so we'll call this initial, U spring at B, or I guess I don't need to use initial because I'm talking about A. So that's really that indicates that it's the initial. B plus UB plus KB. And neither one of these have thermal, so I just left that out of the equation. Okay, so looking here, I have these two, but I don't have any kinetic energy yet. And at B, I don't have any spring energy. And I have both potential energy and kinetic energy. Okay, so I'm going to plug in here. So I'm going to have 1/2 K delta X squared plus mg y. Okay, and is equal to UB, which is mg y. So that's going to be the same. Plus 1/2 mv squared. Okay, and so looking at this, my potential energy here did not change. So I have this on both sides, so I can cross them both out. So I can factor them out. So what I'm left with is 1/2 K delta X squared plus 1/2 mv squared. So I can cancel my halves, and I'm solving for the velocity. So I'm going to divide both sides by m. So I'm going to have velocity is equal to K over m times delta X squared and then square root. So plugging in numbers for that, I'm going to have 80,000 newtons per meter. And notice I didn't write that up here, so I'm going to add that. That's from my figure. So K is equal to 80,000 newtons per meter. Okay, divided by 100 kilograms times 0.5 meters squared for the delta X. And so I get V is equal to 14 meters per second. Okay, so that helped me find the speed after the student was released from the spring, so right here at B. And now I need to figure out how far up the incline the student goes. So what I'm going to do is I can decide I can use one of these, either A or B or C, to figure out the information at D, which will tell me how far up it goes. I don't have the information about C. I'd have to do another step, so I'm not going to do this one. So I'm going to use A. So what I need to think about is my initial energy here at A is equal to my final energy here at D. So I'm going to be comparing this energy bar chart and this energy bar chart. This is at D. So I know I have spring energy and gravitational potential energy at the start, and at the end I'm going to have some potential energy, different potential energy, and thermal energy. And I'm not going to have any speed because it's going to be stopped. So I'm going to start here with C, and I have E initial is equal to E final. So I'm going to have U at A plus, I forgot my spring, so U of spring at A plus U of A plus K at A plus E thermal at A is equal to U of spring at D plus U at D plus K at D plus E thermal at D. And like we said, at A, we don't have K and we don't have E thermal. So these are both 0. And then at D, we don't have the spring and we don't have K. Okay, so plugging in, we have 1/2 K delta X squared plus mg y. And so we'll call this y at A is equal to mg y at D plus, now what is this E thermal? E thermal is really just my force times the distance, right? And so thinking about going up this hill, right, we talked about using delta L. So I'm going to use delta L as my length up the hill. And then the force of friction, right, is what's stealing some of that energy. So I'm going to use the force of friction times along this length, right, which it is. It's in the same direction times the length over which it travels. So that's what my E thermal is, the force of friction times delta L. Okay, so thinking about the force of friction, I need to draw my free body diagram. Here's my person, right? This is where they end up. Force of the normal, force of gravity. Actually, I'm going to put my force of gravity on the left-hand side. And then I've got my force of friction. And I'm going to draw in my components here. So remember that if this is theta, then this is theta. So this is my FGY, this is my FGX. And for the force of friction, I know that's equal to mu times force of the normal, which in our case is mu times FGY. And so plugging in force of friction is equal to mu times mg times, this is the adjacent to the angle, so times cosine theta. So plugging in 1/2 K delta X squared plus mg ya is equal to mg yd plus mu mg cosine theta times delta L. And delta L is what I'm looking for. That's what I'm interested in. So let's deal with YA. So I forgot to put this in my givens, right? It's in the picture. So YA, the student starts at 10 meters. I'm just going to add that back in. Y at A is equal to 10 meters and include it in my drawing, right? So this is Y is equal to 10 meters. Okay, so I need to bring this, what I want is to get this term alone. So I'm going to bring this to the other side. Mu mg cosine theta delta L. Right, I just brought this to the other side, and now I'm going to say is equal to this minus that. 1/2 K delta X squared plus mg ya minus mg yd. Now what about YD? So YD is this distance. So if I'm heading up the hill, this is my theta, right? And this is my delta L. And this is as far as the person gets, this spot right here. Then this right here is my YD. So let's write YD in terms of delta L. And I should have done that earlier. So I know that sine theta is equal to opposite over hypotenuse. So that means opposite is YD over delta L. And now to find YD then is equal to delta L sine theta. So I'm going to plug that in here for YD. So mu mg cosine theta delta L is equal to 1/2 k delta x squared plus mg ya minus mg delta L sine theta. So I'm going to bring this over to this side. So I have my delta L's together. So mu mg cosine theta delta L plus, so I have to add it to both sides to bring it over, plus mg sine theta delta L is equal to 1/2 k delta x squared plus mg ya. So factoring out my delta L, I can also factor out an mg. I get mu cosine theta plus sine theta is equal to 1/2 k delta x squared plus mg ya. And now solving for delta L, I get 1/2 k delta x squared plus mg ya all over mg and then mu cosine theta plus sine theta. And then plugging in, so K is equal to 80,000 Newton per meter times delta X is 0.5 meters squared plus the mass is 100 kilograms times 9.8 meters per second squared. YD is times 10 meters over 100 kilograms times 9.8 meters per second squared times 0.15 times cosine of 30 plus sine of 30. And then we plug that into the calculator, we get delta L is equal to 32 meters.